Okay, on to the next topic, which is relational algebra. Now, it might sound theoretical, but in fact it turns out to be the basis for implementing database management system and query evaluation. Okay, so let's take a look. So, relational algebra, surprise, surprise, is an algebra that works on relations. So in an algebra, you've got operators, you've got operands. In relational algebra, operands are relations. So operators take relations or pairs of relations and return a new relation as a result. There are rules for combining them into expressions, and you can use parentheses like you do in normal algebra, for example. And of course there are rules for how the expressions are actually evaluated. So why do we care about relational algebra? As I said, it forms the basis for DBMS implementation, as we will see in later videos. And as I like to point out, relational algebra operations are pretty much the machine code for relational database management systems. Okay, so we've got an algebra. What are the operations? They're obviously not plus and minus. They're operations that are targeted at manipulating relations. So rename allows you to change the name of a relation or to change the names of the attributes. Doesn't change anything else about the relation, just the name. Selection allows you to choose a subset of the tuples in a table. Projection allows you to choose a subset of the columns in a table. Union, intersection, and difference. We've seen how you might use them in SQL, so they can combine relations using standard set operations. And product and join are very important. Well, product isn't, but join is a very important operation for combining data in tables. And typical extensions include aggregation and group by and what I've called projection plus plus. I basically just mean, so standard projection simply allows you to choose a subset of attributes. Projection plus plus allows you to apply operations to those attributes. So you could add two attributes together, things like that. And the division operation is useful, and we've seen how to implement that in SQL. And in fact, in an ideal world, I would do relational algebra before I did SQL and then explain SQL in terms of relational algebra. But as I've mentioned a couple of times, we've flipped the order of things around here, so we cover the more practical stuff first. Alright, so selection, projection, and join are basically the most common operations. Projection lets you take some columns. Selection allows you to take a subset of rows, and join allows you to take two tables and put them together. And the way you do that is because there are some attributes in common that you can use to decide which pair of attributes should be placed together. If you don't have things in common, you're just going to end up with a cross product, which will be a giant table with not much meaning. And when you add set operations and renaming, you get what's known as completeness in the relational algebra. So basically, an array expression can implement any data extraction information operation that you can think of. Alright, so when you're looking at the textbooks, as if you bought the textbooks, the standard treatment of relational algebra uses Greek symbols. So selection is sigma, projection is pi, and join is this bow tie type symbol. they're a bit annoying to reproduce. Oh, sorry, and rename. It's row. They're a bit annoying to reproduce, so I've actually got English versions of them. So if we're talking about other operations, we will use, intersection, union, and so on, those standard mathematical symbols, unless we're typing into a text file, in which case we'll use multiply for intersect and plus for union. So these are the kinds of things that I'll be writing in relational algebra expressions going forward. That's what they look like in a text. Alright, so that's notation. What about the semantics? And we basically define all these operations in terms of conditional set expressions. So basically we're saying the set of x is such that x satisfy these conditions here. If we want to talk about tuples, this notation here will extract the attributes A and B from a tuple of type T, which presumably has more attributes than A and B. It might have A, B, C, D, E, so we're just going to take the first two. And you can actually write explicit tuple values if you want. Use standard mathematical quantifiers, set expressions, and Boolean operations. And for each operation, we're also going to describe how you might potentially implement the operation. Now, most of the time, this is not how databases actually implement it. If you actually want to find out the truth of that, do COMP3311. So let's take a look. One thing before we start looking at the relational algebra operators, all the operators except things like aggregates return a result which is a relation as well. If we want, we can give a name to the result of a bunch of operations, and then we can reuse it later. So those two things, those two lines there are equivalent to that single relational algebra expression here. Since we've got intermediate results, and these things are relations, relations have to have a schema. The schema will be derived from the schemas for these and depend on what operations are actually used. Alright, so a couple of example databases, very simple example database, just to show how the operations work in a very simple way, and the good old original beer database where we can see how relational algebra might be applied to solve real-world problems. Alright, so the rename operation simply provides a way of converting the schema of a table from one form, so a table called R with attributes A1 to AN, change it to a table called S with attributes B1 to Bn. So we're simply renaming all of the attributes. It doesn't change the contents of the table at all. What it does change is the schema. Alright, so you might say, well, we don't really need rename. Just in a lot of contexts, it doesn't matter what things are called, what the what the attributes are called, so it's not really necessary. However, let's have a look at a relatively complex example. We do a selection and we project out some attributes from that, and then we join with another table, and then we project again, or sorry, we rename to get the final result. So one way we could do that is if we do a single relational operation in each step. We can talk about doing the selection first. We can then apply the projection operation to the first result we obtain. We can then rename. We can then do another operation between the two tables that we defined in the previous two steps, and then we can rename to produce the form of the final result that we want. Now often this gets a bit tedious writing that out in detail, so we might actually use implicit projection. So here we're doing a selection, and it's the result of this coming from table R. I didn't say table R must at least have A, B and C. So we're doing a selection where A is greater than 5, and we're just taking the attributes B and C. Similarly, we're taking S and we're renaming its two attributes to C, C and D, and then we're doing a join on the two tables. If I hadn't done this renaming, I could have actually done a simpler join operation at this step, but there you go. So how does all of this stuff relate to SQL? Well, we could achieve a similar effect by defining a bunch of views. So temp1 could be a view that we define using this kind of selection operation. Temp2 could be a view where we rename the attributes using as. So, and finally we could do a join on the two views, and that would produce our final result. Alright, so that's renaming. It's useful, but doesn't have a lot of semantic content about getting results out from a database. It's just making them look how you want them to look at the end. Right, selection is more interesting. It allows us to choose a subset of the tuples from a table where those tuples satisfy a given condition. Now in terms of SQL, this is slightly annoying, the notation that SQL used, but selection corresponds to the where clause, and the select clause is actually projection in SQL. In any case, so we've got selection here. We take a set of tuples from a table that satisfy a certain condition, and that's how we write the operation. So it's select using a condition C on a table R. And of course C is a test or a Boolean expression, and tuples have to satisfy that. Now one thing we know about this, well, two things we know. The schema of the result is going to be exactly the same because we've simply filtered out rows from a table. On the other hand, the result size may be different if the effect of doing selections is to reduce the number of tuples, and pretty often that is the result of a select. It's possible, you know, if C is the Boolean function true, then the result of the selection, the size of the result of the selection would be exactly the same as the size of the input table. And as I mentioned before, it's got the same schema. So if you want to think about what's happening, so we're building a result set table by table. Now you can think PLPGSQL and return next. But we iterate through each tuple of the input relation R. We run the test on that tuple, and if it succeeds the test, then it gets added to the result set by unioning it into the result set. Alright, so here's some examples of selection. There's our original sample table. If we do a selection where no tuples satisfy the condition, we end up with an empty table. If we do a selection where some of the tuples satisfy the condition, we end up with some results. You can compare the values of attributes. Here we've compared the value of a particular attribute to a constant value. Here we're comparing relative values of attributes. And here we're using an OR condition to pull out the tuples that either have B or C for the value of attribute A. And if we look over here, that's those two tuples there. Right, so all of these result tables are derived from this original table using an appropriate select operation. Alright, what about in the real world? Well, to some extent the real world, if I wanted to find out all about the bars that were in the rocks from my beer database, I could use a selection where the address is equal to the rocks on the bars table. Now, of course, in SQL, you'd write select star from bars where address equals the rock. So the select star basically means don't change the tuples at all, just filter out some of the tuples that satisfy this condition. Alright, if I wanted to find out all the beers made by Sierra Nevada, I could do a select where the manufacturer was equal to Sierra Nevada from the beers table, and then I could do a rename. Apparently I want the result to have, if you like, the column heading beer, and I can do that using a rename on a project from the selected beers. Now in terms of SQL, this would be select name as beer from beers where the manufacturer equals Sierra Nevada. So that would be the SQL equivalent to those two statements there. Right, so that's selection. What about projection? Returns tuples containing a subset of attributes. So X presumably is a subset of the attributes of R. So the results of doing a projection is this, a bunch of tuples that come from R but where we have less attributes. So possibly removing attributes means you might end up with two tuples that were originally different now being the same. So that in theory we could produce duplicates. However, in relational algebra, relations are set, so we never see those duplicates. Of course, we would see them in SQL because it doesn't implement set semantics, it actually implements bag semantics. Alright, so given that we might remove duplicates, then it's likely that the result of a projection could be smaller than the size of the original table. And of course, since we're doing a projection, we're going to end up with a different schema, which has presumably less attributes in it. Right? How do we do that in practice? So we iterate through all the tuples of R. We create a new tuple that has less attributes in it, and then we insert that into the result set by unioning it in. Alright, so here's some examples. Here we managed to project a combination of attributes that happen to be unique, so we end up with the same number of tuples in the final table. Here we do a projection where we end up producing some duplicates, so B and D, 1, 4 there, 1, 4 there, so we end up with less tuples in the final result table, and here we end up with even less. So in terms of SQL, that's like doing select distinct. Alright, so here's what we can do with projection. Get the names of all the beers, so by projecting the name attribute only. Get the names of drinkers who live in Newtown, where we do a selection on the drinkers table. That gives us an intermediate result with the same schema as drinkers, and then we project out the name attribute. And finally, if we want to find out what are all the breweries, even though we know that some breweries make more than one beer, if we do a project on the manufacturer or brewer column, remembering that in relational algebra we're dealing with sets, this is going to give us the set of manufacturers. And Of course, in SQL, we'd simply say select distinct man from beers. Alright, so that's the first couple of relatively simple operations that actually are only acting on a single table. In the next videos, we want to look at operations that act on multiple tables.